We're letting u be a uniform random variable, but now it's going from -1 to 1. That's its support. Then we have another random variable v, which is a function of u, but it's the absolute value of u. And we're taking that times 2 and then subtracting off -1. We're asked in the first part of the exercise to find the distribution of v. And we're going to give its PDF, and we're going to name it in case we have studied it before. And we're given a hint here saying that we should find the support of v and then the CDF of v by reducing it down to the probability calculation of u. After that, we're going to show that u and v are uncorrelated but are not independent, so they're highly dependent. Okay, so let's start by thinking about what v, the support of v is. So we know that u has a support from -1 to 1. That's just given by the definition of u. And then the absolute value of u, well, that has a support of 0 to 1, right? It is always taking positive values. So that is now 0 to 1. V, on the other hand, is defined by this function here. And so let's think about what values v takes. Well, the values of v, we don't know the distribution of it yet, so that's what we're going to take and calculate. But v, we can see it taking values from, let's see, so when when u is 0, when u is 0, well, what's v then? When u is 0, this goes to 0, and then we're left with -1. All right, that's the minimum of the absolute value of u. So it starts off at -1, and then when the absolute value of u is 1, well, then this thing here is 2, and then we're subtracting off 1, so we end up with a 1 here. So that's the support of v. Let's now start by calculating the CDF of v. And that's a little easier, and it's also given by the hint here. It's always easier to find the CDF. I mean, usually easier to find the CDF and then just taking the derivative of that CDF to get the PDF. Right, the CDF of v is defined as let's write f of v. Well, that's just the probability of v taking some little value v. Okay, now we know that v is simply this function of a random variable. And now we have substituted v for u, so hence I like to write that we are in the domain of u now instead of v. So this is a v and that's a u. And +1, just collecting all the terms to the right here. Absolute value of u. Now, opening up this absolute value, we know that the probability of, let's just write a proper v here, a u here, is now between v plus 1 divided by 2. Plus v2, and just to clarify that this is the constant v here, right? So these are the small value v, and I'm going to make this a little larger just to emphasize that fact. Okay, and so this we know how to calculate, right? We know that this has a PDF uniform, and it's between these two constants. So that is simply the integral from minus v plus 1 divided by 2, v plus 1, 2, and the PDF of u over u. And the PDF of u, this we know, is a uniform. So this value here is simply a half. And that's because we have a u that goes between minus 1 and 1. So you can visualize this distribution, minus 1. This is now the PDF of u. That has to be half here in order to add up all the density from minus 1 to 1. And so we have a half here. We have that this thing here is a u going from minus v plus 1 divided by 2, v plus 1 divided by 2. This is simply half v plus 1 divided by 2 minus v plus 1 divided by 2, like so. And this we see is a plus, and the whole thing adds up to being v plus 1 divided by 2. That is the CDF of V. Now the PDF is just the derivative of the CDF. So taking V here over the derivative of V, and that we know that was V plus 1, like so. This is a half. So V has also a density of half. So we can then, and that is, to clarify, a uniform random variable. So this is also uniform, and we know that the support is from minus 1 to 1. Okay, so let's think about the second part here. We're going to show that U and V are uncorrelated, but they are not independent. All right. So here we can, the correlation is essentially correlation of U and V. It's the same as the covariance of U and V divided by the variance of U, well, standard deviation, variance of that. So let's think about what the covariance is here. And so the covariance of U and V is simply the expectation of U and V minus the expectation of U times the expectation of V. Now we know that these numbers here are 0. And that we can see by looking at the PDF here, that it's equal amount of density to the right as it's to the left. So we'll end up by having an expectation of 0. And so we're left with this term here. This term is now the same thing, the expectation of u, but we know that v is 2 times the absolute value of u minus 1, like so. Let's write it here. Same thing as the expectation. We'll pull out this 2 here, that we can do by the rules of expectation, and the expectation of 0 of minus 1 is 0, so we end up with u times absolute value of u, like this. Okay, and so this looks a little complicated. So what we'll have to do, and then we can do, is that we can divide up this thing into the its positive and negative regions, and calculate the expectations therein. All right, so that okay, so we have the 2. Now the expectation, we're going to do the following here. So expectation, we're going to write, let's say this is the plus region. So this is the plus region, and that is now u times u, which is u squared. And then we have the negative region, expectation here. It's u minus u, so times minus u, like this. 2 times the expectation, going from the positive region, which is 0 to 1. And then this is u squared, and then the density of u, du, plus 2 from the negative region up to 0. It's minus u squared f of u, oops, that was an ugly one, du. And we know that this is a half, and that's a half. And so they will cancel these 2's here. So what we end up with is 1/3, 0 to 1. When we evaluate that integral, this is minus the same thing here. Well, we have a minus because of this sign here, so we end up having a u3, 1/3, going from minus 1 to 0. Right? So this whole thing now evaluates to 1/3. And this here we have minus, so we have a 0, and then there is a minus. Okay, let's just write it out. We'll see exactly what's going on. We have 1/3 times 0 minus 1/3 times 3 here, minus 3, 3, which ends up being a minus. So this is a minus, minus times a minus, that's plus, but then we have a negative again. So that becomes a minus. So we end up having 1/3 minus 1/3, which is just 0. All right, it means that the covariance is 0, so this whole thing is now 0. Now, how do we show that they are dependent? Well, because we have just defined v to be a function of u. So v, we know, is highly dependent on the values of u. So knowing u, we will know what v is. So here we see that the correlation is 0, but despite that, they are highly dependent.